Okay, so this is lecture 21. It's the lecture note that I already posted, so I don't need to rewrite everything, but I'll just go through this quickly. All right. So lecture 21 is where we introduce the magnetic field, and we introduce it in a sense of, magnet repelling and attracting each other like this. So it's kind of like electric charge where you have, same polarity of charge repelling each other and then opposite polarity of charge attracting each other. For a magnet, it's kind of the same, but by convention, we don't call it plus or minus. We're gonna call it north and south pole. And if you put north and north together like this, they're gonna repel. And if you put north and south together or south and north together, then they're gonna attract. Okay, so in a sense, it's kind of similar to electric charge, but the one major difference is that you cannot have north or south pole of magnet kind of separately, unlike electric charge where you can have positive charge and negative charge totally separate on different objects. For magnet, you always have to have north and south together like this. If you have a magnet and you cut in half, then the other half will also develop north and south. So you always have this, a pair of magnet altogether. We don't have this thing which is just north magnetic pole or magnetic monopole. It doesn't exist. We don't really know. Well, maybe we know why, but we kind of we have been trying to find experimentally if magnetic monopole exists, but so far no one has found it. I think there's one kind of experiment that claimed that they have found it, but it's just you know one data point and then they cannot reproduce it. So I don't think anyone believe that. But anyway, that's the main difference. For magnetic, usually we're gonna talk about dipole. Okay, so dipole means there's two poles together, north and south, and we can introduce magnetic field, the way that magnet interacts with that kind of field, similar to the way electric charge interact with electric field. For magnetic field, it's gonna cause a rotation of the magnet so that the magnet always align itself along the magnetic field. Okay, so if you have a field which is uniform, let's say in this case going in this direction. Okay, so uniform field means the direction and the magnitude is the same everywhere. The magnet will try to align such that the south to north kind of direction aligns with the direction of the magnetic field. Okay, and we use this as a compass for I think thousands of years. The thing is that the Earth itself is also a giant magnet, where let's say we call this to be the north pole of the Earth, right? So it's a geographic north, and this is south pole, okay, and this is the equator. So Thailand is somewhere along this line, a little bit above the equator, and a compass is a piece of magnet where it's point to the north, right? Pointing to the north means pointing to the north pole. And that being said, the direction of the magnetic field produced by the Earth must also be pointing up like this. So it's the blue one. And for that to happen, the magnet that the Earth produces kind of have to be south here and north here, right? Because otherwise the direction of the magnetic field is wrong. So the whole point is that the geographic north and the pole of the Earth magnet are opposite, and that's just the way we name it. Okay, but you have to kind of understand now. Here is that the magnet of the Earth produces the magnetic field around the Earth, and the compass, which is a piece of small magnet, then reacts to that magnetic field. Okay, so that's the magnetic field. And for a point charge reacting to electric field and magnetic field, they are quite different. The electric field creates electric force like this. So F equal to Q times E. So it's pretty easy to understand because no matter how complicated your situation is, the other thing you need to know is what's the electric field at that point, and just multiply by the charge. Okay, so if you have positive, then it's pointing in the same direction as the electric field. If you have negative charge, then the electric force will point in the opposite direction, and that's it. But for magnetic field, it's a little bit more complicated because we have this cross product between the velocity of the charge itself and the magnetic field vector. So force is Q times V cross B instead of just Q times B, which is maybe what you expect from that. So this gives a few interesting, you know, kind of situation. Well, for example, if you have magnetic field equal to 0, then magnetic force will be 0. This is probably not as surprising. But if the charge is not moving, meaning that the velocity is 0, then no matter how strong the magnetic field is, the magnetic force will also be 0. Okay, so that's, I think, a little bit surprising because you would think that if the magnetic field is very strong, then it should do something to the charge. But it's actually not unless the charge is moving. Okay, so the velocity dependence here is something quite different from the electric field. And the fact that it's V cross B, so it's a cross product. So if velocity and magnetic field point in the same direction, for example, in this case, magnetic field is going up. And for some reason, let's say the velocity of the particle is also going up exactly the same way, same direction as the magnetic field, then the cross product will be 0. So the magnetic force will also be 0. And that's also quite surprising because no matter how strong the magnetic field is, no matter how fast the particle is moving, if they point in the same direction, then the cross product will be 0. So there's no magnetic force. Okay, so magnetic force is, I think, quite complicated in this sense. But to understand this, you need to understand the cross product, which I'm not going to talk too much about this because hopefully this is kind of something that all of you have studied before. Okay, and one important thing is that when you do the cross product here, you cannot reverse the order. A cross B is not equal to B cross A. Okay, unlike multiplying normal number like 5 times 4 equal to 4 times 5. This is not the case here. If you reverse the order of the cross product, you're gonna have the minus sign here. And if A and B, these two vectors, are not perpendicular, then you need to have a factor of sine of the angle between A and B here. Okay, so you can see that even for A and B to be non-zero, if the angle between them is 0, then sine of that angle is 0. So the cross product can also give 0 result, right? So I wrote down here, right? If the angle is 0, then you can get 0. And the cross product is largest when the angle is 90 degrees because sine of the angle has the maximum value of 1, and that happens when the angle is 90 degrees. Okay, so that's going to be mostly the case that we're going to talk about. Like for our case, it's the magnetic force, right? So it's going to be velocity vector and magnetic field vector kind of perpendicular to each other, and then we need to find the force like that. So most of the time, we don't really need to think about this sine of the angle, but keep in mind that it's there. So sometimes you need to think about it. One kind of visual aid that you can use is the right hand rule to figure out the cross product. Okay, so you just take your right hand. It has to be the right hand. If you take the left hand, it will be wrong. You get the wrong direction, right? So you take the right hand, and you have to use three fingers: the index finger, the middle finger, and the thumb. And they are all perpendicular. So this is what we call, like mutual perpendicular kind of configuration. And your index is the first vector, and your middle finger is the second one. So if you do A cross B, then you need to move your hand such that your index finger points in the direction of the A vector, and the middle finger is pointing in the direction of the B vector. Okay, so once you move your hand such that A and B aligns with the appropriate fingers, then the resulting product, which is C in this case, is going to be your thumb. Okay, so it's going to point up. Okay, so A, B, and then C here, right? So C equal to A cross B. Now, if you want to apply this to our magnetic force, or sometimes called the Lorentz force, you have to look at which vectors is the one appearing in the formula. So in this case, force is the product of velocity times, not times, like cross, B, the magnetic field. So you need to put your index finger in the velocity direction, and then the middle finger is always going to be the magnetic field, and the force will be your thumb. Okay, and that's going to be the same as the case where we have not the particle moving but a wire which carry a current. So in this case, your index finger will be the direction of the current along the wire. The middle finger will be the magnetic field, and your thumb will be the force. Okay, so this, if you are not familiar with this, it requires some practice. But once you get it, I don't think there's any problem. So because of the nature of this, it's kind of three dimension, like X, Y, and Z or something like that. It's very hard to draw on a paper, so we use this kind of convention of drawing to indicate whether the B field is pointing into the page, like into the screen that you are all looking at, or pointing out from the page or from the screen. Okay, and into the page we're gonna use crosses like this. Out from the screen we're gonna use dot. With circle or without circle, it doesn't matter, as long as it's not crosses. Then we know that it's pointing out from the page, right? So this is very important. You have to get used to this, because we're gonna draw it like this in the homework and also in the final exam. Okay, so you you should understand what it means. So the kind of most important application of this is what happens when you have charged particle, moving in the region of uniform magnetic field. So you can see now here that in the background you have many crosses, right? So this indicates that the magnetic field is pointing into the page. Okay, and let's say the magnetic field is 2 Tesla, and Tesla is the SI unit of magnetic field. Okay, and then let's say you are looking at the particle at this point here, and at this point the particle is going up with this velocity vector. So you need to find the force, magnetic force, according to this equation. So you use the right hand rule, and you point your index finger up, because that's where the velocity is pointing up. And then you try to rotate your hand such that the middle finger is pointing into the page. Okay, and what you should get is your thumb should be pointing to the left. And then you repeat the same thing for every other point. Like in this case, four points here. Well, 3 other points here. And you're gonna see that no matter where you are, the magnetic force is always pointing into some kind of the center of this circle. Okay, so this makes the charged particle go around in a circle, and this is what we call a cyclotron motion, right? Cyclotron cycle, and tron coming from electron or proton is the particle going around in a circular motion. And we can calculate a few things. Well, first thing is we can calculate the radius of curvature of this circular motion. So you just write down what is the magnetic force. Well, the angle between V and B is 0. Not 0, it's 90 degrees. So sine of 90 degrees is 1. So the force is just QVB. And it's going around in a circle, so it has to obey Newton's second law, especially where the acceleration is given by v squared over r. So you say QEB equal to mv squared over r, and you can get the radius of the cyclotron motion this way. Okay, so you can see that the radius depends on how heavy the particle is, m, how fast it's moving, that's b, and also the charge and the magnetic field strength. What's more interesting is when we try to find the frequency of the motion, right? So we want to find like how, well, first is the period, which is how long does it take for the particle to complete a circle like this. Okay, so it's just the circumference, which is the total distance traveled, and that's 2 pi r. And we already got r in the previous page, from the previous page. So it's 2 pi mv divided by qb here. And the time is just distance divided by how fast it's moving, which is v. So you're gonna see that v cancel out. So the time, the period is 2 pi m over qb. Once you know the period, you can find the frequency. So f is just 1 over t. So f, the frequency, is qb divided by 2 pi m. This is called the cyclotron frequency. And the cool thing here is that it does not depend on how fast the particle is moving, right? So if you have the same particle, one moving slower than the other one, the only difference is the size of the circle, but how how long it takes to complete the circle will be the same. So the rate where this one go around and this one going around will be the same. Okay, and that's very important because we use this kind of technique to kind of figure out what kind of particle that you have in various type of experiment. Sometimes people are looking for new types of particles with unknown charge, unknown mass. But in this case, you put it in magnetic field, you just see, okay, what's the frequency of this cyclotron motion. And in that case, usually B is something you set, so you know B, and that lets you calculate at least Q over M, okay, or the charge to mass ratio, and that's gonna help a lot in identifying what kind of particle we have here. At least if you put some particle in magnetic field, it doesn't do anything, it doesn't go around in a circle, then you can conclude already that that particle has no charge, so it's neutral. So maybe it's a neutron or something like that. Okay, so just to demonstrate, let's say we have an electron in a magnetic field which is 1 Tesla here, and we know the charge, the mass and the charge of the electrons like this. So we can calculate the cyclotron frequency. So F is just QB over 2 pi m. So you just put everything in, and then you get the frequency to be about 28 gigahertz. Okay, so it's extremely fast, oscillation of electrons in magnetic field. And if you replace this with, a proton, then the mass is about 2,000 times larger. So that's gonna make the frequency lower by also about 2000 times. So when one thing is going around 2000 times faster than the other thing, it's pretty clear when you do the experiment. Okay, so in this case, it's a nice way of figuring out whether you have electrons or you have protons or any other kind of particles. So that's cyclotron motion. Um, and then last thing we talked about last time is, okay, what if the thing that we put in magnetic field is not a point charge, but it's actually a wire which has some current passing through. Well, current passing through the wire is also the same thing as saying that there's some charge passing through the wire. So that means the charge is moving with some velocity. And if you remember, the velocity we're talking about here is the drift velocity. Okay. And well, current is associated with, moving charge. So we can do a little bit of manipulation of the formula here. And in the end, you're going to get that the magnetic force depends on the current and how long the wire is and the magnetic field. So these two equations are actually the same equation, but it's just written in a little bit different way. But this one is used when you have a current carrying wire and you want to find what's the force acting on that wire. Okay, so the charge will not go around in circle because it's contained within the wire. So the force will be a little bit simpler because it's just going to the left like this. So it's gonna pull the whole wire to the left. Okay, so you use this formula here. And now we're gonna start talking about this topic of combining electric and magnetic field. So that's gonna be our lecture for today. So let me switch to lecture 22. Okay. Before I talk about the velocity selector thing, let me show you this diagram. So this diagram is the wire, this long vertical wire, and it has some current passing through. And again, this one is to then demonstrate this formula here. Okay, so if you have the wire going up and magnetic field also going up, so magnetic field and L point in the same direction. So L point in the same direction as the current. So the cross product will be 0 for A here. So there will be no force, okay, because L cross B is 0. In order for you to have the force on the wire, you have to have L and B to be perpendicular to each other, like the case you have in figure B here. Okay, so this is, kind of emphasizing the same point that we had earlier, that in order for the charge to experience any magnetic field, the cross product must be non-zero. So you cannot have velocity and magnetic field going in the same direction, right? In that case, the magnetic field will be 0. The magnetic force will be 0, so the charge will just keep on going without having any acceleration. Okay, so that's something to keep in mind. Okay, so for today, I gonna start with combining the two forces. Altogether, it's called the Lorentz force. So the total force will be a combination of electric force and magnetic force, right? So in a general situation, you will have both electric field and magnetic field in the same region. And that's actually going to be the case most of the time because it's actually very hard to make sure that one of the field is 0. But that's not a problem because we know how to deal with electric field and magnetic field. So if we have electric field, the force is just Q times the electric field. This is what we learned already many weeks ago. And then if you have magnetic field, then you just add this velocity dependence part. So it's just something like this. Okay, so this gives you the total force on the charge, and usually it's gonna make, you know, trajectory of charged particle very complicated. But we're gonna look at one special case where these two contribution to the total force actually cancel out. And that can happen when you have electric field and magnetic field going perpendicular to each other. Okay, so you can imagine that, let's say you have a region where the magnetic field is pointing into the page like this. So again, crosses means magnetic field going into the page. So I will write here B field into the page, right? And let's assume that we have a stream of particle, meaning a particle just going through this region with some velocity. Okay, maybe, well, just one particle will be enough actually. So if you just have this, and also we need the charge. So let's say it's a positive charge, so plus Q. Well, actually, let's just draw it in the center here. So plus Q here. So velocity going to the right, magnetic field going into the page, right? So again, you need to convince yourself that the magnetic force will be pointing up. Okay, so we cross B if you magnetic field, magnetic force going up. So I will use this color maybe. FB going up, right? If the charge here is negative, then FB will have a negative sign, so it will go down. That's the only difference. Okay, so it's not too complicated if you have, you know, opposite polarity of charge. But anyway, if you have just the magnetic field, the particle will experience a vertical force. In other words, force pointing up. So what's going to happen to the particle? Well, the force going up will turn the force upward, turn the particle upward. So the particle will just, instead of going straight, it will just go up like this. Okay, because it's getting bent. And well, this is nothing but just a small section of a circular motion that we talked about just now. But we don't want this, let's say, we want the particle to just keep on going straight. So you somehow have to cancel out this magnetic force. And you don't want to touch the magnetic field, but you have this extra knob to play with, which is the electric part. So what you need to do is to make the electric force cancel this magnetic force. And you can do that by simply applying electric field in the downward direction. Okay, so we're gonna draw with orange color here. So this is E field going down. When the electric field is going down, the electric force will also be going down because Q is positive. So this will be Fe. So you can see that if you choose the electric field and magnetic field appropriately, then Fe and Fb can be made to be equal each other. And when that happens, that means the magnitude of the electric force is equal to the magnitude of the magnetic force like this. Okay, and that happened when QE equal to QVB. So charge cancel out, and you can see that is E equal to V times B. So in other words, looking at looking at this situation differently, if you fix E and fix B, then the only velocity of the particle that experience no force is when V is equal to E over B, like this. It doesn't matter what's the charge of the particle, it doesn't matter what's the mass of the particle. If the velocity match this condition, then the particle will just go straight. So if this condition is met, then particles will have no deflection. And this is where in some experiment, especially particle physics experiment, we use this as a velocity selector. And the reason why we want this is because velocity of the particle is associated with the kinetic energy of the particle. So in a sense, you can select the kinetic energy of your particle for your experiment this way. So how exactly do people apply this? So it's called velocity selector. So let's say you have the source of particle, maybe it's like a hot oven with some opening. And the thing is that the particle coming out will have, a variety of velocity. So some will be slow, some will be fast. But you want to select, or you want to filter such that the only velocity that you want enters the experiment. So what you can do is similar to the picture that I drew above. So you just set up a region with cross magnetic and electric field. So essentially setting up a velocity selection, or actually I want to say velocity selector. Okay, so you set up B field and E field like this. And my electric field, let's say, going down. E field. Okay, so we can also put in some number. Let's say we put in electric field to be equal to, let's say, 10 Newton per Coulomb, or 10 volt per meter. Okay, either unit is fine. And then we put in the magnetic field to be 0.1 Tesla, okay, which is not too strong. It's comfortably producible by normal electromagnet. So what is the velocity that meet this condition? So V equals to E over B. So V is just E over B, so it's equal to 10 divided by 0.1. So that's going to be 100 meter per second. Okay, so what it means is that this streams of particles coming out will have a broad range of velocity. If the particle has the velocity close to or exactly 100 meter per second, that particle will just go straight 100 meter per second. What happens if the velocity is a little bit less? let's say 90 meter per second or 80 meter per second. If you look back at this equation, if you have less velocity, the magnetic force part will be less, but the electric force will be unchanged. So that means the force going down will be unchanged, but the force going up will be less. So that means if the velocity is too slow, the particle will get bent downward like this. So this is v less than 100 meter per second. Okay, and again, the reason is because the downward force is the electric force coming from the electric field. That's unchanged. Okay, so it's bent downward. But if the velocity is larger than 100 meter per second, then the magnetic force will be stronger, will be too strong, and it will bend upward like this. So this is v larger than 100 meter per second. So what you need to do in the experiment is you just need to make kind of like a shield, and you just punch a hole in between, in the middle of the shield like this, right? So that anything not going through the hole will get filtered out, right? So in this case, you can make sure that the only thing that survives is the velocity that you want, 100 meter per second, like this. Okay, so this is a velocity selector, and if you want to repeat the experiment with different, velocity, then you just change one of the field here, and you will have a different velocity. So it's actually a very convenient way of, making sure that you have the velocity that you want. And it's quite simple in principle. In reality, it might be a little bit complicated because you have to make sure that the electric field is uniform, the magnetic field is uniform, but the physics is as simple as what we are talking about here. Okay. All right. So let's move on to actually the last topic, which is how to produce a magnetic field. And we will talk about two things, which is the Biot-Savart law and the Ampere's law, and one application, which is a solenoid. And then we are done with the material. Okay. So just to make sure that I finish everything in time, I might not have a break, a 10-minute break today. So forgive me for that because I don't want to take a break and then maybe run overtime. So you can, take a break later. So I will just continue then. So the next is how to produce magnetic field. Right. So we have talked about, how the charged particle reacts to a magnetic field by writing down the Lorentz force here. But the question is like, okay, how do you make the magnetic field in the first place? We know already how to make the magnetic field. You just take a piece of magnet which has north and south pole, and then automatically you just have the magnetic field coming out from the north and going into the south pole like this. Right. So this is what we call permanent magnet. Permanent magnet. It's a natural occurring magnet that you can, pick up in the forest sometimes, I think. But it's not too strong and it's probably not as useful as you might want it to be. So we need to be able to artificially produce a magnetic field. And a physicist named Faraday, Michael Faraday, and you probably have heard his name a few times already, figure out that in order to produce magnetic field, you can actually pass the current through. And later on, like the guy named Ampere kind of figure out the quantitative way of producing magnetic field from a current. So there will be a lot of names, and then sometimes you're confused. Okay, like who is the one that figure all this thing out already? It's hard to say because back in the day, you kind of have different scientists working independently, and not all like theory in physics are well established. So it's kind of like here and there, and then at the end it's Maxwell who combine everything together, right? So I'm also not an expert in historical you know detail about the development, but the kind of the fundamental law that we use is actually, I want to go to the next page. The fundamental law is something like this. So essentially what we know is current produces magnetic field. So essentially if you want a magnetic field, you just need a current. And what is a current? It's actually just like charge moving. So exactly how do we calculate that? So let's say we have a wire, not necessarily a straight wire, but in any case it has a current going through the wire given by I, like this. By the way, the formula that I'm gonna write down is called the Biot-Savart law. It's gonna look quite complicated. I'm gonna say now that it's not gonna be on the exam. Okay, so you don't need to worry about like doing the integration. But later on, a simpler case which is Ampere's law, that's the one that you need to know. Okay, so this one you just you just know that this formula exists, but I don't expect you to be able to use it to derive complicated stuff. But if it appears in the homework, maybe that's possible, but it's not going to appear on the final exam. I can guarantee you that. Okay, anyway, what do we have here? Well, the thing is that you need to divide the wire into a small section. So let's cut it this way. And just look at this small section. And we're going to call this DL, small section DL, with a vector sign. So it's also a vector pointing along the wire like this. Okay, so a different point will have a different direction of DL. But in this particular case, it's pointing that way. And we are interested in a magnetic field at some point away from the wire. And this point will be indicated by a vector R. Actually, just a unit vector. A unit vector R is the unit vector pointing from the section of the wire to the point that you're interested in. Let's call it point P. And the distance from that piece of wire to the point that we are interested in, let's just call it R. Okay, so this R is the distance. This R hat is the unit vector pointing to point P. And the magnetic field at this point will be the magnetic field produced by just this small section dl. So I will write it d of B field to indicate that it's the magnetic field created from this tiny section of the wire. If you want the total magnetic field, you need to add up all contribution from every section on the wire, and you need to do the integration. Okay, so it's kind of similar to how we integrate electric field from a wire, where we divide the wire into different section and then you just integrate it. This turned out to be equal to some constant here. I will talk about this in a few moments. That's not so important. The important thing is the one that follows, is the current times the small section of the wire dl. Also, don't forget the vector sign. Cross with the unit vector r and then divide by r square, like this. This is called the Biot-Savart law, and it's the go-to formula if you want to calculate the magnetic field. In terms of applicability, this one is actually more useful than the Ampere's law. But again, because of the nature of the formula is mathematically quite complicated, so we're not gonna spend too much time talking about this. Okay, so this is a Biot-Savart law. Let me talk about this thing for a moment. So mu zero, so this is a Greek letter that we call mu, 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 okay. Mu zero is called the permeability. And subscript zero means it's for vacuum. It actually does not mean much at this point because it's just a constant at this point. If you look at a different material, for example, magnetic field is in not vacuum but in in iron or in some other material, then this value of mu will change. Okay, so that's gonna be the case where this becomes relevant. But here you can just treat this as a magnetic constant or something like that. It's kind of like in Coulomb's law when you have k q1 q2 divided by r square, the Coulomb force, right? Whether you're gonna call this k or you're gonna call this 1 over 4 pi epsilon 0, it doesn't really matter because it's just a constant. Okay, so don't worry too much about this one. So in order to calculate the magnetic field, you need to integrate this. Actually, just to be sure, let me just put in the value of mu zero here. So let me put it here. So mu zero is about 1.256 times 10 to the minus 6. Okay, with SI unit, which is Newton per Ampere square. In case you cannot find it somewhere else. All right. The magnetic field again is just the integral of the magnetic field dB. So it means you need to integrate this Biot-Savart law, IDL cross R divided by R square, like this. And just to demonstrate how to use this law, let's calculate a very simple case, which is, let's consider a circular wire with radius r with current going around counterclockwise like this. And we want to know the magnetic field at the center of this loop. This is the case where we need to apply Biot-Savart law. Okay, so the first thing to do is to pick a point, let's say here, and this point gonna be our DL, so it's pointing that way. Okay, so zoom in a little bit. So that small, maybe I'll use a smaller thing here. So that is our vector DL, and this point to the point at the center, which is what we are interested in. So this is d, not d, this is r hat. Okay, this is the unit vector from this section pointing to the center of the loop. And the radius is r, that's kind of given by the question already. Actually, let me change this to big R just to be clear. Okay. The first thing we need to figure out is the direction of dB, which is the magnetic field coming from this small section dl. So let's just write the Biot-Savart law here. So dB is IDL cross the unit vector r divided by r square. Okay, and you can see that dl cross r give you a direction of b dB going out from the page. Okay, so dl is that way, r hat is that way, so that means the magnetic is going up like this. Not going up, sorry, coming out from the page. So dB here out from the page. Okay, not into the page, it's out from the page. And it's gonna be the same no matter what section or what point on the circle that you pick. Okay, so in that sense, we kind of take care of this part already. So we know that the magnetic field will be pointing out from the page. So the rest is just to integrate the magnitude of the magnetic field, since the direction will be all the same anyway, right? So the next step will be a bit easier. So dB, right? No vector sign here because we already know the direction already. So it's mu 0 divided by 4 pi. And current stays here. dl stays here. And the cross product to the unit vector r is just gone because that's used for figuring out the direction already. So we don't need to repeat that here. And then divide by r squared. What is r squared? R is the distance from this section of the wire to the center. And it's always going to be the radius of the loop. So it's going to be always r squared, big R squared, which is a constant. So in other words, integrating this will be quite easy because there's nothing to integrate other than just dl here. So integrating dB will be mu 0 over 4 pi I divided by big R squared. So I took everything which is a constant out from the integral, and I have not dt dl, I have only this thing left here. That's the thing that I need to integrate. So the total magnetic field, or the total magnitude of the magnetic field, is mu 0 divided by 4 pi times I divided by r squared. And then the integral of this is just adding up all sections along the circumference of this circle. And it's just adding up the length, which is easy because it's just the length of the total circumference, which is 2 pi r. So the blue thing becomes 2 pi r. So the magnitude of the magnetic field is just mu 0 I divided by 2r. And the direction is out from the page. Okay, we already figured that out already. So that's it. That's how we calculate the magnetic field at the center of the loop. Okay, and so this is an example of how to use Biot-Savart law. in a more complicated case, you need to be a little bit more careful about the direction of the cross product. But in this case, it's easy. Okay, so it's just to demonstrate how it can be used in this simple situation. All right. So what about next thing, which is called the Ampere's law? The Ampere's law is kind of like, well, if you remember, you have Coulomb's law and then you have Gauss' law for electric field. This is kind of like that. So it's kind of a different way of, quantifying magnetic field which is produced by a current. So let's see what it is. And it might be a little bit hard to imagine, so I will go a little bit slowly here. The Ampere's law also describes how magnetic field is produced by a current inside a wire. So again, let's say we have a wire. Let's make it thick like this. It's a continuous wire, but I need some gap here because that's how I want to draw the stuff. So you have a wire which carry some current I, let's say going up like this. Okay, for the Ampere's law to work, you need to set up a closed path, okay, or a closed loop. For example, you might set up, you might set up a path which is a circle around the wire like this. Okay, that's badly drawn. Let me try again. So it doesn't have to be a circle, it just have to be a closed loop. A closed loop or path. Okay. And imagine this as, like a loop, and then you kind of stretch some kind of paper along the loop. It's kind of like a drum, and then you have like a drum head, which is a flat surface. So you set up the loop such that the current is going through this surface, right? It's piercing, going through this surface. That's the wire here. Okay, so you set up this closed loop. Once you have done this, the Ampere's law says something like this. If you take the magnetic field on the path, I would do this B field. Let's say at this point here, okay, the magnetic field from the wire will point in this direction, and then here it will point in a different direction, something like this. Okay, no matter what direction the magnetic field is along the path, what you need to do is you need to take the dot product between B field and a small section along the wire, which is called dl, and you just have to integrate along the closed loop, and that's where this circle comes in. So it's just an integral sign with a circle here to indicate that, okay, you just need to integrate for the whole loop, not just the section of the loop. So that's what the circle means. Okay, so the circle here means integrate along the whole loop. It's the loop that you choose here. So once you have done this, this will be equal to mu0 times I, the current. And this thing is the Ampere's law. And you are very confused now what this means. And that's fine because this is, in a sense, quite abstract. So there's some, diagram that I need to show you in the next page. But before I do that, let me explain again what I'm trying to do here. Okay, so you have a wire, which is the green thing here, and you set up a loop Okay, it has to be a closed loop. So it can be very big. How big you want, it doesn't matter, right? As long as it's closed. Closed means you have to end up where you begin. You cannot set up the path, which is something like this, and then stop here. This is not a closed loop. This is not what we want. Okay, it needs to be closed. And once you have that, then as you walk along the loop, okay, you just take the magnetic field that you get at any point on the loop, and then you multiply by the direction that you're walking, and you just accumulate B dot dl, which is the product of magnetic field and the displacement that you walk, and then you just accumulate it until you end up with the whole loop. So you end up where you start. You're gonna get mu 0 times I. So let's see how it works. Um, this is kind of like the situation that we talked about earlier. The thing that's gonna be helpful here is also what we call the right-hand rule. It's also the right-hand rule, but it's the different one that you had earlier. So this one, the right hand kind of wrap around the wire like this. And this is used to figure out the direction of the magnetic field around the wire. Okay, so we're gonna kind of use this when we use the Ampere's law to figure out the magnitude of the magnetic field. So let me go to this diagram first, actually. So this is a nice diagram because it shows clearly like the three-dimensional kind of aspect of the whole thing. So you have a wire with no current first, and the wire is going through a piece of paper. So you can say that the wire is perpendicular to the paper, right? So this is how we see it. So imagine that's to be the case. And you put many tiny compass on the piece of paper, and the role of the compass is to measure the magnetic field. Once you start passing the current through the wire, then the compass will stop pointing to the north, but it's gonna point like this in a circle. Okay. So this is what we mean by magnetic field going around in a circle. It doesn't mean that the vector itself is a curved vector or something like that. It's just that if you look at this point here, the magnetic field point in this direction. Okay, and then if you move a little bit here, the magnetic field will point, perpendicular to the circle, and if you're here, then the magnetic field will point that way, that way. That's what we mean by field going around in a circle, right? It's just that every point on this path, this circular path, the magnetic field is, going, tangential to the circle. That's what we mean, like this. Okay, and to apply the Ampere's law, you can see that since, well, remember how we use Ampere's law? You set up the path, and the best one to use is the circular one, which is already shown here. So imagine that you walk along the path. So you start here, and your role is to walk along this circular path. At every step that you take, what you do is you measure the magnetic field that you are feeling, and you just take that magnetic field, multiply by the direction that you're walking, and in this case, the direction that you're walking and the direction of the magnetic field is always the same direction, right? Because when you walk around this circle, you are walking in the direction which is always tangential to the circle. And the magnetic field is also always tangential to the circle, right? So the magnetic field and the and the direction that you're walking is always the same. Okay, so the dot product is always going to be just B times dl. So let me be a little bit more specific here. So I want to erase this. Okay, so let's say this circle is distance r, actually small r, from the wire, right? And that's going to be a distance r from the wire at every point on the circle, right? Because that's the definition of a circle, right? And again, you're walking on the path. So to apply the Ampere's law, sorry, I'm trying to give myself a nice space here. So we need to do the integral of b dot dl, right? And that's going to be, again, the magnetic field dot with the direction that you're walking. But for our case, b and dl always in the same direction. Okay, so we can forget about the dot product, because if b and dl in the same direction, remember what the dot product is. It's quite a while. It's when you calculate the work done by the force and displacement dot together, right? So you remember that there's like a cosine of the angle that appears, and in this case, cosine of 0 is 0 degrees, because b and dl points in the same direction. So it's always going to be 1, right? So this integral becomes just integral of b times dl, and we don't need to worry about the direction any longer, because we know that the direction of the magnetic field is given by this figure here. Okay, so it's just b dot dl. And the magnetic field is probably constant in terms of magnitude everywhere on the circle, because everywhere on the circle is the same distance from the wire. So you can take this out from the integral, like this. And what is this again? Well, this one is the total length of your path, which is a circular path. So it's just the circumference of the circle. So it's just 2 pi times r. So the closed loop integral of b dot dl becomes b times 2 pi r. And that's equal to mu 0 times I, because that's what Ampere's law says that, right? So in this case, we easily shown that the magnetic field from the wire is equal to mu 0 times I divided by 2 pi r. So this gives you the magnitude of the magnetic field, but the direction of the magnetic field is given by this right-hand rule. Okay, so it's going around in a circle. So you can see that it has 1 over r dependence. So the further away from the wire, the weaker the magnetic field is, but it's not weaker by 1 over r squared. Some of you might expect this, because for the Coulomb force or the electric field, right? So if you remember, E from a charge is kq divided by r squared. But for magnetic field from a wire is actually 1 over r dependence. Okay, so it's going down a little bit slower compared to the electric field. Okay, so this is how we use the Ampere's law. And in the homework, you have 1 or 2 questions that you know give you an opportunity to practice using this. But again, the important thing is that you need to identify the current here. Okay, if you have the current which is double, let's say 2I, let's say you double the current in the wire, then this one will be also double. Okay, so if you double the current, the magnetic field will also be double, which I think makes sense because how strong the magnetic field is depends on how strong you have for the current. Okay, and the direction follows the right hand rule, right? So it's going around like this if the current is going up. You should verify by yourself that if the current is going down, so you reverse the current direction going down here, then the magnetic field will go around in the opposite direction. Okay, so that means the magnetic field at this point will go this way, this point will go that way. Okay, so your right hand will need to flip upside down, right? So your thumb will always pointing in the direction of the current. Okay, so again, this is the right hand rule, but it's a different hand configuration from what you had earlier. But again, remember to use right hand. If you use left hand, then it will be the other way around, which is not good. Okay, it will be wrong. Yes, here, here. Okay. All right. Um, the last topic we're gonna talk about is actually an important application of Ampere's law, and we're gonna talk about magnetic field from a solenoid. But first, let me talk about some other things. So these are three configurations that you probably will see most often, and the thing is that all of these in principle can be calculated using Ampere's law, but in some case it's gonna be quite difficult. So that's why the expression for the magnetic field is given here. So let me just tell you a little bit what it means. So this one is what we just calculate in the previous page. Okay, it's the magnetic field at a distance r from the wire, and using the right hand rule, you will see that the magnetic field above the wire is pointing out from the page. So that's why you see dots here. And the magnetic field below the wire will be crossed, meaning that it's going into the page. Okay, so if you're confused how the right hand works, imagine this case and then flip it 90 degrees so that it's going sideways. And your fingers will give you this magnetic field direction. But the magnitude of the magnetic field is given by this. So you can see that it's 1 over r dependence, just like what we calculate earlier. Okay, so that's for a straight wire, and we use Ampere's law to calculate this. And then the other one, we kind of calculate this using the Biot-Savart law. In principle, you can also use Ampere's law to calculate, but for some reason, it's just very hard to do. B center here is the magnetic field right at the center, right? So this is a flat coil. Basically, what it means is just a circular loop. Wheel sideways, it looks like this. Okay, so it's the magnetic field right at the center. And it's mu0 times n. N is the number of turns. The one that we calculated earlier has n equal to 1 because it's only one loop, so one turn. So it's mu0 I divided by 2r, which is exactly what we did earlier. Okay, and the last thing we're going to talk about is a solenoid. A solenoid is essentially just a flat loop, a flat coil, but not just one turn, but multiple of turns. So it's kind of like a coil that you expect to see. It looks like something like this. So I'm trying to draw. I hope this is clear what I'm trying to draw. It looks like this. So it's kind of like a loop. It looks like a spring, but we are not talking about its like spring property here is just a multi-turn coil. And because of this, you can think of each loop, each each turn to be something that looks like this, right? So you have like multiple turns, and each one gonna produce a magnetic field given by this picture. So when you add everything up, the magnetic field inside the loop, inside the coil, will be mostly straight like this, right? So make sure you can imagine how to go from here to this picture, right? You just stack up multiple coils together, and then you're gonna see that the field inside is a straight line, which is uniform, more or less uniform, and it's gonna be equal to mu zero times small n. Small n is the turns per length of the coil of the solenoid, and then times the current I. Okay, so for this last few minutes, we're gonna use the Ampere's law to actually prove this formula, and that's gonna be it for the material that we need to cover in this class. Okay, so what we're gonna do? Well, we're gonna cut this in cross section in half, right? So when we do that, you're gonna have some coil on the top and some coil at the bottom like this. Okay, and I'm gonna put in dots here. This red one actually indicates the direction of the current, which is out from the page. Okay, remember this is when you cut the whole coil in half, right? So if you have, something like this, then you cut it in half like this. Okay, that's what I'm doing. So the coil loop around, and that's why the direction of the current is coming out from the page for these guys, and it's gonna be into the page for this guy here. Okay, these are direction of the current, not the magnetic field. We're trying to figure out the magnetic field, but this is the direction of the current like this. Okay, and it's a cross section, so imagine that you have like the whole loop like this. Okay, but I'm not gonna draw that because it's too crowded. So I want to find a magnetic field inside the coil, and we already have some kind of hint that the magnetic field is going in the horizontal direction. So let's cheat a little bit, and let's say we know that. Okay, let's say B field is going to the right like this, and our task here is to figure out what is the magnitude of the magnetic field. Okay, so we're gonna use Ampere's law. You don't need to use Ampere's law. You can also use the result from a single loop and then add up. You have to integrate them all together, but it's quite complicated. So in this case, Ampere's law is a lot easier to use. So how to do that? Well, the first step is to define the path, the closed path that we're gonna apply the Ampere's law. Okay, and the path we take is gonna look quite strange, but there's a very good reason why we do this. So we're gonna take a path which is a rectangular path, and we're gonna put it a really, really long one, and then close the path here. It's actually gonna be so long that you can think of this as infinitely long rectangle. Very long. Okay, so what's the purpose of this? Well, because we know that the magnetic field is going to the right inside the solenoid, And we also kind of know that outside the solenoid, the field is very weak. Even if the field is not zero, then most of the time, oh, actually it's gonna go this way. Most of the time, the magnetic field you have outside will go horizontal to the left like this. And then maybe there's some magnetic field here, right? But this magnetic field, so let's talk about this bottom magnetic field here. So B field here is approximately close to zero if we take this rectangle to be very, very long. So for a very long rectangle, so that means B dot dl here, I'll write it here. So we can say that B dot dl here means this section here is equal to zero. It's because the magnetic field is very weak when you go very far away from the solenoid. And there's nothing preventing us from doing that, so we are fine. But then we have three other sides to figure out, which is this side, and this side to calculate B dot dl. But here and here you can see that the direction of the magnetic field and the direction of the loop is perpendicular to each other. So B dot dl here is zero because B is perpendicular to dl. Okay, so what I'm trying to do here is I'm trying to calculate the integral of B dot dl along the path that I drawn here, a rectangular path. And in order to do that, I need to calculate B dot dl for every section on this loop. And I already argued that the three sides of the rectangle give me the B dot dl equal to zero. This is zero because the magnetic field is zero because it's just so far away from the coil. This side is zero because B dot dl, B and dl are perpendicular to each other. Right? Because dl, when you walk, it has to go down or it has to go up, but B is going sideways. So the dot product is zero. It's 90 degrees. So the only section that gives me non-zero B dot dl is the one inside the coil, which is here, right? So now you see like why I set up the rectangle path to looks like this, okay? Because then the only thing that survive and give me non-zero B dot dl is just this tiny green section here. And the magnetic field is also uniform, so that means the magnitude and direction is constant. So if I choose the length of this rectangle to be L, then B dot dl is just B times L, the length of the top section of the path that I chose. And that's equal to mu 0 times I from the Ampere's law. So then we say that the magnetic field is mu 0 times I. Oh, sorry, I need to say something here. Well, what is this I? This is the current going through the loop, which is this area here, right? So you need to count like how much current going through this loop, this path. And the amount of current going through depends on how many wire going through this area, right? So if you talk about the solenoid in terms of, let me step back a little bit, in terms of this number n, small n, which is the number of turns per length, then the number of turns of the wire I have enclosed by this path, n, which is turns enclosed by the path, is equal to, so n equal to the length, which is L, times the small n, which is turn per length, so NL here. So each wire carry current of I, so the total current is just big N times I. Okay, so I'll write it down here because running out of space here. So integral of B dot dl equal to mu 0 I, this is Ampere's law, and it's just B times L, right, just the top section here, equal to mu 0 times the total current going through this path, which is N, small n, times L, times I, which is the current for each wire. L and L then cancel out, which is good. Because remember what is L? L is some kind of arbitrary, width of this rectangle path. And it's something that I kind of like made up, so it shouldn't depend on it in the end. So B is equal to mu 0 times small n times I. That's the magnetic field. That's the strength of the magnetic field inside a solenoid. Okay. I mean, in the exam, you can just use this formula. I don't mind that. But just remember that this small n, that's not the number of turns. Okay. That's the number of turns per length. Right. So it's like, for example, if you have like the whole solenoid to be, 10 centimeter long, and then this 10 centimeters, you have, let's say, 100 turns, then small n is 100 divided by 10. Okay, so it's 10 turns per centimeter or something like this, right? Not the total number of turns. So that's something that I saw quite frequently. People use this formula a little bit wrong because you forgot that this n is turns per length, not the total number of turns. Okay. So this is the field inside the solenoid. The field outside the solenoid, well, this is, let me write that this is inside the solenoid. The field outside the solenoid, usually we say it's approximately 0. It's not really 0, but it's very small compared to the field inside. So most of the time we just forget about it. Okay, so well, that's it for the material that we need to cover for the exam. I have quite some time left, but I think that should be enough for us. So at this point, maybe if you have any question, you can ask now. But if not, then we can stop here today. And the session on Wednesday will be the review for the final exam. And the final exam is set to be on the 26th. Okay, so you have quite some time to, go over the material. And you still have, the last homework due. Okay, so the last homework will contain magnetic stuff. So make sure that you take a look at that at least. Well, at least take a look at the solution of the homework. The solution of the homework 5 and 6 are already posted. And so you can take a look at that. For 7 and 8, I will do it after the due date of the last one. Okay, but in any case, well, that's it for the material you require to know for the final exam. So if you don't have any other question, then I will see you guys on Wednesday then. All right. So, okay, if you have any question, you can ask now. If not, then you're free to go.